All right, guys. So let me introduce the speaker, Dr. Avimanyu Sahoo. Did his electrical engineering from Missouri University of Science and Technology in Rolla, and Masters of Technology from IIT in Varanasi, India. He is an assistant professor in the Electrical and Computer Engineering Department at the University of Alabama, Huntsville. His research interests include learning-based control and its application in lithium-ion battery pack modeling, diagnostic, prognostics, cyber physical systems, and electric machinery health monitoring. So he's developing intelligent battery management system for lithium-ion battery packs used on board electrical vehicles, computation, communication, efficient distributed intelligent control systems for cyber physical systems. So, Abhimanyu, is there much of car manufacturing where you are?
We don't. We have Mazda, Toyota nearby. We have Mercedes also near Tuscaloosa. So we have quite a presence of automotive here. But mainly this town is more of NASA and defense. We have the Defense Missile Agency here, and
Yeah.
Army here, FBI here. So we have kind of all aerospace companies around.
Okay. So, well, the talk is on real-time learning embedded next generation of battery management system for electric vehicle safety. This is an energy systems is a huge area, very fast-growing area. So, I think it should be good for the class to learn about this kind of computer science. So, Abhimanyu, all to you.
Yeah, thank you, sir. I'll go ahead and share my screen here. So can you see my screen now?
Yep.
Hey everyone. I know I'm a little off track in the sense I'm from electrical engineering. I work in batteries, and you might have a question saying that what I'm doing here in a computer science seminar. Before that, let me introduce myself again. I'm Avimanyu Sahoo. Currently, I'm an assistant professor at University of Alabama, Huntsville. So during my talk, I'm going to talk more about electric vehicle battery management system. We all heard about EVs. That's more popular nowadays, and everybody wants to own one Tesla for sure. I strongly believe that everyone wants one. This is the future generation or future transportation system. So I don't know. I believe by end of this lecture, what would be my objective here to let you know what exactly the most important or critical part in an electric vehicle is a battery management system and how it works and what we do to make it more smarter. And that smartness part comes from computer science. That's what I'm here for presenting. We'll talk about real-time learning. It's a little off track than the normal, back propagation-based training algorithms. We'll talk about physics. We'll see how physics being embedded and how we can, as we go, how we can learn different things for batteries. So if I cover my topic, I'll talk about little physics of the batteries. I'll talk about what a battery management system is and talk about how can we model battery using physics. I will talk about how we can find failures or faults inside a battery. You might have heard about all fires and other incidents, here and there about electric vehicle. Then we'll talk about how we can embed learning in the systems and then some future work. Before that, if I want to summarize my expertise for last 15, more than that, years, I'm working on intelligent control. When I say intelligent control, the controls are for using neural networks for developing controllers. When it's not the same deep. When I started, deep learning was not that. I mean, it not been started. So all earlier days, we are talking about a single layer, 2-layer, or 3-layer neural networks to do this control kind of stuff. And it started around 1990s when these things being transferred to control systems with the neural networks. So we'll talk about my main research focus was how can I reduce computation for while training these algorithms. That's the goal. That's my thesis also. But it is applied to a dynamical system perspective. I also work with some image processing stuff, some reinforcement learning, and battery management system. So the core of my research stay in controls area. Then this AI or other AI is a tool for me to use it. But the difference, if you look into our work in a dynamical system or control theory perspective and a general machine learning, we more talk about convergence proofs, we talk about stability guarantees, more analytical way of thinking about all this, rather more application oriented. So let's get back to the topic. We all see electric vehicle, but we heard that there is a battery pack. It's a very big battery pack, which is actually very heavy also and most expensive part of the vehicle. And mostly they're on the chassis. So technically, we are sitting on these batteries in an electric vehicle. That picture tells you about that. So the whole idea is when we think about an electric vehicle, we want the vehicle to travel from point A to point B or your destination with a full charge. That's all guarantee. And also when we stop at any gas station, now I'm saying charging station here, so we should be able to fast charge it faster and go forward. So these are two of the major challenges in electric vehicle research. And you might have seen all this kind of stuff happens. I don't say that all electric vehicle catch fire, but there are incidences already happened. If you talk about Chevy Volt, Chevy Volt is the smaller, a little smaller size car, now very popular actually. They in 2016, I think they launched their first model. After that, they got 17 fire incidents. Some of them are attributed to battery, and it's because of the battery manufacturing. I'll talk more details about that as I go forward in the lecture. There is not even a single company who manufactures EV have not given a recall that their battery is fully safe. So that means there is something here we can do as in academia and as a researcher to improve the safety of these things. And let me put into numbers that should make you sense. When I'm talking about a life of a battery, it is usually 7 to 8 years. People say, up to 12 years max. And it is the most expensive part of your car. Technically, if your battery is dead, then you replace the battery, it would cost 40 to 50% of your cost. So that's most critical here. Now, when we go back and talk about these EVs, we more of talking about high energy density because we want to drive 300 miles like a gas driven car. So what we are looking into lithium batteries, and lithiums are not very nice. Okay. So lithium batteries catch fire very quickly. But the good thing about it, if you operate those lithium batteries to 20 to 35 degrees, or this is not minus, it is 20 to 35 degrees. If you operate in 20 to 35 degrees C, they're absolutely perfect. That means that's why we could able to our cell phones, our laptop computers in perfect conditions, nothing happens. The problem comes when the temperature either goes sub-zero or high temperature. If the temperature goes sub-zero, there is a phenomena called lithium plating. So everybody knows in a battery, we'll have a cathode, we have an anode. Now, when these ions move from the cathode to the anode, and you do keep on charging at sub-zero temperature, they got plated on the anode. So what happens is these are metals. When they got plated, slowly, gradually they increase. They pierce the separator because between the anode and cathode, there is a separator. They pierce it. You can look that here. So if you look here, they pierce the separator and touch this cathode. And if they touch, there is a fire. We call that internal short circuit. There are also other phenomena. If I go back and charge at a higher temperature, then something called SEI is called solid electrolyte interface. There is a layer formed on that on the uh, anode, and that takes out your capacity of the battery. So these are challenges if you operate in low temperature and high temperature. You might have heard about these things like I think this year in the winter, every state got snow, correct? And every place there is sub-zero temperature, and these Teslas are sitting for longer time to get it charged. It's very difficult to charge them at sub-zero temperature, and that's one of the bigger challenge we are trying to handle here. A tiny battery, which look at it, and you see that millions of multiple different types of fault inside it. If I want to make it safe, it is better I go and figure out how these faults happens, understand them, and try to detect them before anything happens. Actually, the standard, I think the European Commission standard rule is that's a 5-minute notice. If something happens, your battery management system or your car console should tell you that run away from this car within 5 minutes. 5 minutes is good enough time. We stop a car and go out and save ourselves. That's the whole goal here. When I'll talk about fault detection, I'll talk about that if I can tell you that there is a fault happening and there is 5 to 10 minutes time for you, then we can save our life. That's the whole goal here. Now, what is this battery management system? So we have cars at home. They are lead acid or NIMH batteries. They are very safe. You charge, you overcharge, you over discharge. It really doesn't matter. But lithiums are not like that. Lithiums are very sensitive to overcharging, over discharging. I mean, so when I say over discharging and under discharging. So we have to maintain those balances properly. And I also talked about if nowadays the goal of the companies is how we can charge it faster. So something when I say charging something faster, what does that mean? I connect it to a high power charger and it forces higher amperage to the battery, which the battery cannot accommodate itself because you are trying to force these electrons through this battery, and it's kind of pipe. You cannot take more than that. If I in a layman language, if I speak about it, so faster charging will also degrade your health. So those kind of management, and one of the most important one would be the thermal management. Whenever the battery operates, there will be heat. If there's a heat produced, somebody has to identify that. Somebody has to manage the cooling system such that they stay in their normal operating temperature and we enjoy our safe ride. So that's the whole point. And all these functionalities being handled by a system, that's actually the control system where I come from is battery management system. Yeah. Any question up to this point? So now what exactly we need from here? We saw there are several incidents happening, fire happening, another thing. So we have to make this battery management system more autonomous. Or maybe add some intelligence to it so that it can do a health conscious decision. So the goal comes back to here is how can we embed intelligence in these batteries? If everybody see a battery, what are they? There are two terminals, positive and negative, correct? We can measure voltage, current, maybe the surface temperature, but the thing happens inside the battery are many things. So our goal is using these three variables, what we can measure, how can we do all of those things? So that means we'll look into the physics of the battery. So that means we go back, the goal would be go back and model the battery using its physics so that we can, with these three measurements, if we can extrapolate the internal behavior, which I call states of the battery, if you might have come across state space in some of your controls classes at any point of time or signal systems classes, if you have taken one. We call states of the battery, the internal states of the battery. And then if we can estimate the internal states, we can talk more about it. So the whole idea to make a battery management system smart is to use a model of the model can be a physics-driven, analytical model, or it can be a data-driven model also. You can develop a deep neural network and train with many data and put it inside in the battery management system. The other functionality we need to know about is how to detect internal fault. And when I say internal fault, I'm talking about detecting a fault when it just initiates, because it doesn't give us a time. Like one of the effect called thermal runaway in battery. So it's at some onset temperature, when the temperature keeps on rising, when it is at a threshold point, after that, it says it goes to thermal runaway. Nobody can control it. The only way is just burn, and now the bigger challenge is extinguish a battery fire. So for the fire community, the battery fire is a new type of fire. So it might be seeing a little bit strange when I talk about fire, for extinguish this car or gas fire, it took us 60 years to understand that how can we extinguish these gas fires. Now we are having a new fire called lithium fires, and we don't have any actually clue about it. How can we handle about it? So that's the point. The point is, if before it gets into that state of onset temperature when it leads to a thermal runaway, if I can detect it. And that's the goal of this talk. And we'll see that how can we use the learning stuff here or the neural network stuff here to get into that point. Let me go a little more technical, okay? So if I look into a battery, you take a battery, you know there is a out terminal voltage, there is a current flowing through it. When that means it's kind of an electric circuit. The simplest model people come up with to model a battery is just a 2 RC circuit. So I have one RC here. These are represent the transient behavior of the system, a battery, and this is the internal resistance. And you can consider this as the source of the voltage, how the voltage is coming. So this is the generator voltage, and then there is some drop, and you get the terminal voltage. When I charge the battery, the current goes inside. When I discharge the battery, the current comes outside. That's the point. Now, when I'm talking about thermal, if I want to model it thermally, so we can do abstraction here. We can consider the thermal resistances here, and we can model that. So there are two things to understand about thermal modeling. I have a core temperature. Core temperature is the temperature inside the cell, which I cannot technically measure, and I have a surface temperature. And all these things are dynamical. When I say dynamical, that means I have to use some differential equation, either ordinary differential equations or partial differential equations to represent the dynamics. And that's the physics part of the thing. This is not all, because one of the bigger problem I mentioned before, that the battery kills itself in 7 to 8 years. So that means the life is very small and it degrades faster. So let's say I come up with a model like this. I find the R0 when the battery is new, these resistance values, the capacitance values here. As the battery keeps on degrading, these values keeps on changing. Now, initially, I put this model in the battery management system, and it keeps on predicting the value. And now, after some time, it is not going to work. So that means I need an update mechanism that keeps on updating the parameter. Interestingly, it turns out that these parameters are actually, even in the healthy conditions, are not constant. They are function of the state of charge. State of charge means how much charge is there in a battery, or the state of the health, or temperature changes. These parameters keeps on changing. So this is a kind of a very tricky situation here. If you say that I accurately estimate using a model, is very, very challenging in this point of time. If I go a little more details, these are some of the simple equations we use, differential equations, to model the battery. The first one is the circuit I have shown you. The second one is your thermal model. TC stands for core temperature. TS stands for your surface temperature. And now the third one is the capacity fade model. When you use your battery, the capacity keeps on fading. You start the battery, let's say it's 3 milliampere hour or 3 ampere hour battery. After some time, and nowadays you have the smartphones, Apple has very nice software. If you Google, get into the battery software, it says your life or 90% capacity is left, or 70% capacity is left. So interesting fact is, a battery, if the capacity goes below 80%, we have to discard the battery. So the life of a battery is from 100% to 80%, not more, not below that. So we have a 20% play to do that. And this equation, actually, this is an empirical equation. This is being derived based on experiments that how the capacity loss happens. Now, if I want a battery management system to make a decision, so what is the purpose of this model? I can use it and put it in the battery management system. This is a computer software. So it gives me predictions. I have a battery, and this is a model. If both of them are matching, this model output in a simulation, battery output in real life measurement, if they're matching, everything is going perfectly fine. If they are not matching, then the real battery has having some issue. And that's where I'm trying to take you there. So, but if I take these three different equation models, they depend on each other. Technically, if I look into the interactions, they look like this. This diagram is not looking very nice. The point I want to make here is you have the center in the thermal model, the capacity model on the right side, and the left side is your 2 RC model. They are all interlinked. So if I take three different equations and do it, I cannot do it. So in our first, when I started working on this, we looked into how these coupling things happen. The red terms you see here in these equations, these are some of the couplings. So we went back and tried to modify these dynamics so that we can integrate it. Now, what this model can tell us? This model can tell us at certain time, at certain current level, if I'm charging or discharging the battery at that point, what would be my capacity in 5 years or in 10 minutes, correct? And then it also gives me the core temperature and surface temperature. Interestingly, I mentioned like I only can measure the terminal voltage, the surface temperature, and the current. These three things I can get from a battery, nothing else. But if you look into this model, I have so many things. I have the voltage across the capacitors, I have the state of charge, I have the core temperature, and also capacity. These things I cannot directly measure. When I cannot directly measure, but these are important indicators for me to decide safety of the battery. So that means I have to go back and use the physics of this or come up with a model and try to predict all these values using these models. And we call them as observers, if you might have studied in controls class. So we formulated this model, and that's our first work we did in our lab with my PhD student. And then we went back and compared with the if you just take those models without coupling and now with a coupled model, what is the difference? If you look into the first cycle, there is no difference. Perfectly fine. After some cycle, because our model is more coupled and the degradation level is based on the capacity fade happening. So you can see in the middle of the cycles, when I say cycle is completely charging and discharging. In general, a battery can go up to 3,000 cycles. Again, don't count on that number. It depends on what battery you purchase. So in the middle, we see this started different. And then we try to run it for the whole cycle. Here we're till the time it reaches to 80%. Remember, I said the health dies at 80% is the limit, cutoff limit for us. So how many cycles our coupled model did is 4,520 cycle. A uncoupled model is 3,664. So technically what is happening is if you are using an uncoupled model and your life becomes 80%, you only have used 3,600 cycle. It's a wrong information if you use a more accurate model, the one we proposed. Okay, so that it is almost like 100 cycles. So this is a significant improvement. We saw that. We looked into these are all simulations. Then we said, okay, is this that make sense with experimental data? So there is a NASA data set there available. NASA people did a lot of experiments on that. So they kind of give us some data. So we kind of run that, and we got close. Our model gives 405 cycle, where the coupled model get 457, uncoupled says 405, and it was matching with our model, matching with the NASA's experimental evaluation. So now the point is how the actual battery behaves. The model is exactly behaving like that, in a sense that we are tolerable errors. So this model is ready to deploy in a battery management system for prediction purposes. And what we are predicting? We are predicting the core temperature, which is more critical to detect any thermal changes happening. We are also estimating or predicting our SOC, state of charge, so we can tell that how far the car can go. Now with this accurate model, we can tell better. If you use an inaccurate model, then you have a margin of error is low. Now this is all about the physics of the battery. We also went back and tried this in our lab. So if you do this model testing, there's a bunch of tests we have to carry out. This one of the tests called is open circuit voltage for SOC test. And then you have to go back, identify these parameters. You remember I talked about all these capacitors and resistances. We need to find those values of the battery. So we cannot directly measure them. So we need to run some test and we extract those parameters. So these are called HPPC test, some pulse tests here. And then we went back and took a real drive cycle. This is how the waveform looks, the charging current looks in a vehicle when you drive in a urban area. And these are available online. So we kind of took that and we put it into our model. And we also measured from our battery. We have a battery test bed here. So same current we apply to the battery, same current we apply to the model in our computer, and we kind of compare these results. You can see that they're fairly okay. The temperature doesn't look okay, but if you see the numbers, it's 25.1 and 25.2, it's 0.1 difference. It's within It's actually within 2 to 5% band. So it was really okay for us to say that our model is fine. So what is the purpose of this model can happen? We can do is we put this in computer, this software, the mathematical equations, and we take a real battery, and we keep on comparing these two outputs from the model and the battery. If there is a deviation between this output, the computer the changes thing is not changing, but something wrong happening in the battery, so that's where a deviation. And that's called the detection methodology. In general, this is called model-based fault detection methods, and which I'm going and talk about in a minute. So what our goal is, okay, so we have a nice model. If the battery is healthy, the goal is the model output and the battery output will 100% match. Not, I mean, say with reasonable accuracy, it will match. And I shown those plots for you. Now, let's say the battery having an internal temperature rise. It can be because of many reasons. Maybe some internal side reactions happening. It's an electrochemical system. So some temperature starts going up. So if some temperature starts going up, so that means there is a thermal resistance is increasing. That's why the temperature is going up. So that will reflect on the battery voltage. It will also reflect on the surface temperature, later in the surface temperature, but it will be faster in the core temperature. So the whole idea is if I want to detect that temperature rise inside the battery, what I can do is whatever model I designed, this I write it as a fault detection observer, and the cell, if I take these two outputs, you can see is VT, terminal voltage, surface temperature, and the estimated value coming from the model I developed, and I compare with a threshold. If the difference between these two greater than some threshold, then I can say there is a fault happening. And this is more important, okay? What kind of fault and what, it is not very important for us when I have to give a 5 minutes warning that this battery is going to catch fire. So detection is very, very important. So now if you look into the accuracy of the detection, it completely depends on this model, what we are using here. Okay, but you will say that if model is not 100% perfect, if the model is not 100% perfect, what else we can do? That we can change this threshold and the battery will also keep on degrading. If I go back and say battery is degrading, I can develop some thresholds just here, which are function of time and a function of the degradation values, and we call them adaptive threshold. So we kind of design some adaptive threshold. When the battery degrades, your threshold value keeps on changing so that you don't reach to the false alarm side kind of stuff. But once I detected the fault, so what is the next thing? So let's look at some of the results here. I was saying that if the battery is healthy, and my model is always healthy because we have that model, and these red lines are here are the threshold, and this blue line is the difference between the battery voltage minus the model voltage. You can see they're very close to zero because of the model accuracy. And these red lines are my thresholds. They're between the thresholds. So as long as they're within the threshold, battery is safe. Everything is working perfectly fine. I'm not worried about anything. Now, coming back, if there is a fault happens and we kind of simulated a fault, you see that residual started crossing these thresholds. And I've shown you that these thresholds are not constant. You can see these lines here because they're adaptive. They keep on changing based on the model uncertainty and battery degradation type of thing. Now here I can say I detect it. Oh, that's the first step. Now, till now, I never talked about learning here. You'll ask me the question, okay, why this lecture about learning? Now, what makes this residual go up? Initially, when I modeled the battery using those equations, they only counted for healthy condition. Now something changed inside the battery leading to fault. So that means my equation must be changed. So that means how I can go back and write it. If, let me go back to those two equations here. So this is my healthy battery equation. Okay, so I consider that as my battery. And this fault detection observer, it actually uses the same equation here, but there is a little bit of part here, which L times Y minus Y hat. This counts for the terminal error so that we can match the states. This is standard observer design. So now this part and this part is done. And the next slides talk about the thresholds here, which I talked about the threshold value, and see the thresholds are also a differential equation here. So they are dynamic, they keep on changing. Once I got that, and I see that there is a fault happening, so there is something changing in the battery. And let's look at that, how that affects our model. Now, this was my observer, this top part of it, and with this L prime C. Now, there is something happened inside the battery, so the dynamics changed, which we never modeled. Now, if I want to detect how much it is, what is being changed, what I did is here, to this dynamics, I added a neural network here. It just says theta transpose phi. You guys all know about it. We write it, some weight times some activation function or basis function. So that's what it says. And this is just a 2-layer neural network. Remember one thing is don't go with a deep neural network architecture. We don't really need it for this function. For learning some of these functions, we don't need. We just use universal approximation property. A 2-layer neural network is good enough for us. So we added it in our model. We added a neural network here. So when the battery is healthy, the top part and this L part was there. Now battery is faulty, this part. So the fault will be equivalent to this part. And you'll ask me how. These are being understood. Like if I have a core temperature is rising, the dynamics in the core temperature will change. Because some multiplication and addition term will show up there. So you consider that as a function. So we added this neural network here. So technically what happens if you look at the picture, so this, our total fault detection observer becomes this observer plus this observer, but this neural network part only kicks into the circuit when there is a detection happening. So here I say fault is detected, then you trigger this neural network. That means you add this part to the equations, and this neural network, you keep on training it. And that's more important part, which will be interest of to you, that how I train this. And I'm talking about a fault is now happening. I'm not collecting fault data to train it. So that means I go back and train it online with time for going forward. So that is how we do it. So we went back and developed a update law here. Theta hat, this is a differential equation that everything is in continuous time. You might have seen things like theta k plus 1 goes to something like that. Okay, so but the bigger problem is here. What data I have to train these neural networks? The voltage measurements, the current measurement, and the temperature measurement. Where the fault is happening? At the states. And how many states I have technically here? I have 7 states. I have 3 input. There is a dimension mismatch here to train these neural networks. So to avoid that problem, we kind of did one thing, that we have a healthy observer. If you see this hat portion, we borrowed these 3 parameters from them and added the faulty parameters here, 2 faulty parameters and this 6 estimated parameters. We use that as the training data and use them to train that. The problem here is, again, you will ask me a question, where is the target value? If it's a supervised training, where are the target value? We don't have target value. The only thing in your case, if I ask you a question, you can figure out the target value here. I mentioned that this observer should be exactly same as the battery when it is healthy. Now, when it is faulty, I added a neural network. So if the neural network is learning it properly, then the total output, these X values, should match the battery output also after learning. So that's our target. So what is the target? The residual should be pushed to 0. So that's what the whole idea here. So we trained this neural network. You can see it here. If you look at here, we started triggering the fault here, and the threshold in the blue line goes up, touches the threshold. That time we trigger the neural network. Once the neural network starts learning online, and when it starts learning, it starts matching with the battery output. Now the faulty battery and the observer also becomes faulty. So the residual started coming down to 0. That's the amazing part of it. What is the advantage of it? Now, if this comes back to 0, then the part we added the neural network is nothing but the fault function, what is happening inside the battery. If I get the fault function, can I train it? Yes, I can train it. I can find out if I have a limit for the fault, okay, after this is going to, I need to leave. Actually, I can calculate how much time it is going to take to reach that point. And that is the goal of giving you a 5 minutes warning to come out of the work. So this approach uses both the model and the neural network to do that. And we run quite a bit of experiments on this. We tried with the multiple different type of faults. In all the cases, if you see the trigger happens here and then in quick time, in like in almost like if you look like 100 seconds, we could able to learn that function and get back into inside the threshold values. So that fault function is in our hand. We can use it to extrapolate and finding the remaining useful life. So that's one of the applications here we use to make the BMS smarter. Now learning is online. You don't need data offline, collect data, because the biggest challenge with fault, how to create a fault. I want to create a fault inside the battery. That experimental process is way more difficult. So the only solution could be if I'm getting new data online or in time series data, can I learn it as I go? That should be the goal. But the point is, when I started talking about the electric equivalent circuit model, like electric circuit, that really doesn't speak about the internal chemical changes. If you can model the battery with the internal chemical changes or chemical reactions or the transport equation and whatever we call, then it would have been better. But it turns out that those equations look like this. They are partial differential equations, because now you have to not only count for your time, you are counting for space too. So if you studied about numerical solution of partial differential equations, we have to discretize the space and use, solve these equations to get the concentration. C is the concentration is the lithium, how much lithium is there. How much lithium will tell you what is the capacity of your battery. So if I want to find the concentration, I have to solve this equation in the battery management system. And you are talking about a battery management system is not a big thing or a big computer. It's just an embedded board. And it doesn't have so much of computational power to real-time calculate these numbers by numerically solving it and discretizing the grids. That's not feasible. So the newer approach some of you might have working now is called physics-informed neural network. The whole idea is I'm not going to discretize it anymore, but I can use a neural network to approximate the solution to this equation, which solution would be the C, the concentrations here, but that abide by the constraint enforced by the dynamics. So if I want to do that, so what let's say this is the simplest PD you can write it. So your neural network should do two things. One thing is this difference. So the left side minus the right side should be equal to 0. We should have some boundary conditions and initial conditions. They must be satisfied. If they're satisfying, then I can force the physics into the neural network. Now the neural network learn the physics, but always, as I mentioned, that always be model uncertainties. So that means we also need to match the data. So what people usually do, they have a loss function they define, which embeds the physics, this equation, the error between these two variables, left and right, and the boundary losses plus the data losses. So you have a true value and you have a target, then you embed that and try to do that to learn that so that you learn the solution perfectly. So, but in general, what is the problem here? All the work in the pin sector is the focus was to solve this equation, just to find C. But when they do that, there is a challenge here. I say boundary losses and this charging and discharging current, they're actually boundary functions. They use some fixed current to do that. And though if you have a pin and you learn the solution, you cannot use it for prediction purposes because there is no current. The current is never being used as the input to the model. I mean to say, if I go back to this diagram, that makes more sense here. So this is my neural network. It's just a feed-forward network. There is nothing big here. This I part is not there. We don't need the I part to solve for the partial differential equation. I have the space variable and time variable. And I just try to force these equations, make sure that when I define the loss, I have the PDE, I have the initial, I have a boundary. I force that and I use the backpropagation to train it offline. Because this is physics, I can simulate the data. I can use simulated data to learn it. But if I do that, now if you ask me, okay, if the charging current is 10 ampere, can you tell me what is the concentration at so and so on time? I cannot do that because I do not have a current as input till now. So this year, what we thought, okay, let's try feeding a current as an input. And then if I make it current as input, then actually I can use it as a prediction model. Surprisingly, we got good results on this here. But the whole idea for us was use online learning, the one I mentioned earlier. So we only train this neural network with physics only. So we enforce the neural network with physics. And as we go, we added this part where we frozen the last other layers and only train the last layer for this 4-layer network to learn as we go any changes, like different C rates, like your currents are changing, so you need to learn with a different current. So we try to do that. When we learned only physics, we could, and this orange line is the numerical solution.